Okay, welcome everybody. It's my pleasure to introduce today's speaker, Adeline Samson from the University of Grenoble. She's an expert on several things, among others, stochastic approximation, expectation maximization. She has been doing several works on inference for hypoelliptic diffusion with an interest in mathematical neuroscience. And today she's going to talk about computational statistics for neural mathematical models. Thank you, Adeline.
So thank you, Massimiliano, for inviting me, even if it's not a real life invitation. And thank you for being here. So I will present some several works with a lot of different people from Linz, Copenhagen, Caracas, Warwick, Paris, and Irene is also from Linz. So I will start with what is the data I'm focusing on. So I'm working with intracellular recording data of one single neuron. So I don't know what you already know about the behavior of a single neuron. So basically you have the shape of the neuron, and what we are able to record is what we call the membrane potential. So it's a difference in voltage between the interior and the exterior of the cell. And we can have high frequency data of this potential. And you have a plot here of a typical recording of a single neuron. So like the potential is somehow stationary, and at some point you have a spike, so a very high increase of the potential, and then you go back to the stationary behavior again, and you start again with the spike. So, and when you start a spike here at this point of the phase, this shape here until you come back is almost deterministic. And between two spikes, it's stochastic. The behavior is stochastic. And the time you start a spike is also stochastic. As you may see, so here we can say at this level, you start the spike. And for the second one, maybe the level is higher. So the behavior between two spikes is stochastic. The time at which you start this deterministic shape is also stochastic. So what is the objectives when you work with this kind of data is to try to understand the spike emission. And for that, we want to study some mathematical models, and especially we will work with stochastic models. And these stochastic models are parametric. And the last step will be to talk about estimation issues of these models. So a typical neuronal model for this intracellular data is a deterministic Maurice-Lockhart model. So the Maurice-Lockhart model tries to describe what happens at the membrane of the neuron. So here in orange you have the membrane, and you have gates, different kinds of gates at the surface of the neuron. And when these gates are closed, the ion channels cannot enter the neuron, and when they are open, you can have some exchanges between the interior and the exterior of the neuron. So Maurice-Lockhart model describes three types of gates: calcium, potassium, and what we call leak gates. And for each of these three terms, we model. So VT is potential, the membrane potentials, and you describe it with a reversal potential, so VCA, VK, VL, and these G's parameters GCA, GK, GL are what we call the maximal conductances. And a last very important quantity is CT, which is a proportion of channels, of gates that are open at time t. And then we have a second equation which describes the behavior, the dynamic of this proportion, which is just this very simple equation. You have alpha, the rate of opening channels, and beta of closing them. And it's just a proportion between 0 and 1. CT is a proportion between 0 and 1. Okay, so this is a deterministic version of Maurice Lockhart. Then some stochastic versions have been proposed. The first very intuitive stochastic version is to describe the opening and closing behavior of the channel as a stochastic variable. So for each channel, you can introduce a variable, and then you introduce C and T, the proportion of channels among the n channels which are open at time t. And then you just have two states, close and open, and you model the transition between these two states with the rate alpha and beta as before. So here between a jump, when Cn stays the same, the trajectory is described by this deterministic equation as before, and then you can have a stochastic jump for Cn. So this is what we call a piecewise deterministic Markov process. It's very difficult to study this class of PDMP, piecewise deterministic Markov process, and especially in statistics. When you want to estimate the parameters of this PDMP, it's very difficult. So my way of working with this data is to consider what we call diffusion approximation or Langevin approximation. So what you can prove is that when n, the number of channels, is large, then you have a weak law of large numbers. So you can prove that the PDMP converges in probability to the deterministic Maurice Lockhart model. And you can also approximate this process when n is large. So it's a large population approximation. You can more or less apply a central limit theorem, and you obtain a diffusion approximation. So the first equation is exactly the same. I just replace CNT by CT, and CT is described by a stochastic differential equation, where here you have a stochastic part with a Brownian motion. So the drift is the same as before, and you replace the jumps. When you have a large population, the jumps are small, but you have many of them, and then you can replace that by a Brownian motion. So it's a Langevin approximation. So here, sorry, do you see still my, yeah? Do you see my screen? Yeah, I guess so.
Yes, we do.
Okay, so here you have the two components, V, so the membrane potential. Sorry, do you see my mouse? I can't see my mouse anymore. Okay. No matter. And then on the right part is the description of CT. It's written U, sorry, it's C. Okay, so it's what we call a typical hypoelliptic stochastic differential equations. So it's a diffusion of dimension 2, driven by only one Brownian motion on the second equation. So we can write sigma, the diffusion matrix, as degenerate. So it's a vector of dimension 2 with 0 on the first component because you have no noise acting directly on VT, and sigma for the coefficient the second component. So usually VT is what we call a smooth component, and CT is a rough component because the noise, the Brownian motion, acts directly on CT. But what is nice with this diffusion when it's hypoelliptic, and what does that mean? That this hypoellipticity, it means that the noise from the second component propagates to VT. And this happens that the noise propagates to the first component when the drift of the first component, B1, depends on C. So you just need the condition that the partial derivative of B1 with respect to C is not equal to 0. So then the noise will enter through C in VT. And in that case, you can prove that the stochastic process VT-CT admits transition probability with a smooth density, even if the diffusion matrix sigma is degenerate. Okay, so that was the first model, Maurice Lockhart, which is, if you remember well, highly nonlinear, because alpha, m infinity, and beta are nonlinear. And another neuronal model that we like to study, because it's much more simpler, is the Fiji-Nagumo model. So it has been widely studied in the neuronal literature. So you have the same two equations, no noise on the first equation, a noise acting only on the second equation, CT. And you have less parameters. It's almost linear. This system is almost linear, except the cubic term VT on the first component. And on the plot, you have also an example of trajectory of this process for some nicely chosen parameters, epsilon, s, beta, and gamma. Okay, so just to show you, to give you an intuition of the problem of hypoellipticity versus ellipticity. So ellipticity is when you have two Brownian motions acting on V and C. So just to show you, so the first column you have no noise at all. Then the second column you have noise only on V. The third is noise only on C. So that's the models that we will study. And the last column is when you have noise on V and C. So the elliptic case. So depending on the origin of the noise, you may have spikes, reproduce spikes or not. So hypoellipticity may have a consequence on the generation of spikes. Okay, so what are the properties of this Fiji-Nagumo model? So it's more easy to study than the first model, the Maurice Lockhart. So one point which may make things difficult to study is the fact that the drift of the first equation is only locally Lipschitz and not globally Lipschitz. And in the work we have done with Massimiliano and two other colleagues, Evelyn and Irene, this was the main part, the fact that the drift was only locally Lipschitz. Then it's hypoelliptic. We have nice Lyapunov function. We can prove it's ergodic, and we have a unique stationary distribution. And also the process is beta mixing, which may be nice when you do non-parametric statistics. And just to finish with the presentation of the model, I just want to, it's not a neuronal model, this one, but just to say a few words about another class of hypoelliptic system, which is this class that you have here, which is called either stochastic damping Hamiltonian system, Langevin equation, or hypocoercive model, depending on the literature. So here it's much more simple because you have only, the first equation is dvt equal ut dt. So it's just the derivative of v that you describe by a stochastic differential equation. And the good news for us is that the Fiji-Nagumo model enters this class if you introduce ut as this transformation. So I just take the drift of the Fiji-Nagumo of the first equation of the Fiji-Nagumo, and then you, by Ito formula, you obtain the equation for u, and you can prove that it's exactly an example of this stochastic damping Hamiltonian system. And what is nice also for this model is that you have a lot of properties that have been proved, like the existence of a Lyapunov function, the stationary distribution, ergodicity, and beta mixing. And again, in some cases, you really need the existence of these properties to continue working and developing statistical methods. Okay, so what are the objectives of the talk? First, I will present you some numerical approximation schemes, because usually we don't know the exact solution of the stochastic differential equation, so we need to approximate the solution. And I will present two classes. A first class of schemes based on Ito-Tailor expansion, and the second class is what we call a splitting scheme. Then I would like to explain why parameter estimation is more difficult when we work with hypoelliptic SDE, and also when we have only partial observations, because the key point with this intracellular data is that we only observe V and not the second equation of the diffusion. And then I will introduce different strategies to try to estimate the parameters. So one is based on particle filtering coupled to stochastic approximation EM, and another one that I've just starting working on is optimal control. So, but first we need to be able to simulate and to describe the solution of the diffusion. So again, we work with this kind of diffusion. So we have two coordinates, B1 and B2 are usually nonlinear, and we have noise only on the second equations. So then later in the talk, I will use the notation xt for the two-dimensional process and b of x for the two-dimensional drift. And then you can just write the SDE like this. So again, when b is nonlinear, you don't know the transition density, and you have no exact scheme to simulate a solution. So you need to approximate the solution of the SDEs. So what do we expect from such an approximation? We would like, so if I write x tilde as the approximation obtained by a scheme, a numerical scheme, what we would like to have property of convergence. So what usually what we study is a mean square convergence. So you just study the maximum of the expectation at time ti of your discretization process, discretized process. So if you discretize the process with a step size delta, and you denote ti all the discretization times, then you would like that the difference between the true solution x and the approximate solution x tilde is less than a constant times the step size delta at the order p, and this is in expectation. Okay, so that's the first point. Then if you already think in terms of the statistical objective, we will use computational statistics like MCMC, particle filter, EM algorithms, so iterative algorithms that will require to evaluate the solution of the diffusion a lot of times. So we need a scheme to approximate the solution, which has a very low computational cost. This is really crucial when you want to do statistics on these models. And then obviously we want to preserve what we have called structural properties like hypoellipticity, ergodicity, and also properties about the oscillations, the spike emission. So the class of models that I will present you are Tailor expansions, a scheme based on local linearization, which is very close somehow to the Tailor scheme, and then the class of splitting schemes. Okay, let's start with the Euler-Maruyama scheme. So here you just take the SDE and you discretize the drift with delta B and the diffusion coefficient with square root of delta times the diffusion coefficient sigma and a random Gaussian vector. In the case of hypoelliptic system, it does not work. So it's not mean square convergent, but some alternative and variant have been proposed, but it does not converge. This simple version is not mean square convergence. And what is more important, it does not preserve the hypoellipticity in the sense that the approximation you obtain has not a smooth density for the transition density, the transition probability. So then what we have studied with Susan Ditlevsen from Copenhagen, we have considered a higher order Ito-Tailor expansion, which we have called a 1.5 scheme. So instead of just looking at the first order approximation of the drift, like delta B, we have higher order terms for the drift and also for the diffusion coefficients. So you can see the diffusion matrix here, sigma tilde. So here, what we gain with respect to the Euler-Maruyama scheme, so it's not mean square convergent, but at least it's hypoelliptic in the sense that the noise from the second coordinates propagate to the first one. And if you look at the matrix here, sigma tilde, you can see the order of the noise. The order of the noise for the second coordinate is delta, and here it's delta 3, because you need more times for the noise to propagate to the first coordinate. Okay, so then there's another class of scheme which is called local linearization, which has been studied especially for hypoelliptic system and also with statistical purpose. So what is the idea? The idea is that you approximate the solution by a new autonomous linear SDE on each interval of the discretization scheme, and you approximate the SDE by a linear version where you instead of the drift B of X, you just use Tailor expansion around the current value X tilde at time Ti. So I will not enter into the details of the formula. What is nice in that case is that on each interval, what you need to solve is a linear stochastic differential equation. Because it's linear, you have an explicit solution, which is of exponential form. And the covariance matrix, it's exactly the same as the 1.5 scheme presented just before. So here what you get is hypoelliptic. It's mean square convergence because of this exponential form, but it does not preserve the other structural properties. Okay, and the last type of scheme is the class of splitting schemes. And that's what we have studied with Massimiliano. So I will describe this splitting scheme on the Fiji-Model example. So if you remember well the Fiji-Model equation, you will recognize that here we have just split the original system in two subsystems. So here we have a linear stochastic differential equation. So we just keep linear terms here for the drift, and we have the noise. And for the second subsystem, we have the nonlinear part for the drift and no noise. So this one, what is nice is this one is linear. It's a stochastic differential equation, but linear. So we have the explicit solution of this subsystem. And for the nonlinear part, we have no more noise. In the specific case of the Fiji-Model, we have an exact and explicit solution of this deterministic equation. And if it's not the case, you can use at least numerical scheme adapted to ordinary differential equations. Okay, and then the main idea is that, so I will denote XA delta, the solution, the exact solution with a time step delta of the first subsystem, and then XB delta, the solution of the second one. And what is a splitting scheme? A splitting scheme is when you compose these two solutions step by step. So the literature version of the splitting scheme is when you just compose the solution of the first one with the solution of the second one. And what we call the string splitting scheme is when you compose first the solution of the second subsystem with time step of delta, half delta, then the first one, and then again the second one. Okay, and these two schemes gives you two different ways of approximating the stochastic differential equation. Okay, so what is very nice and what we have proven even in the case of only locally Lipschitz drift is that the scheme is mean square convergence. It's one step hypoelliptic. It preserves the Lyapunov function. It preserves also the ergodicity and the phase and the oscillations of the system. The only thing that is quite difficult is that the transition density of the scheme may be highly nonlinear due to this nonlinear ODE. And so we don't have a look at developing a statistical algorithm using this scheme, but I guess that the fact that the transition density is nonlinear will be difficult and will make the algorithm more difficult. Okay, and just to compare, so here you have a comparison on the Fiji-Model between the splitting scheme and the 1.5 Ito-Tailor scheme for different time step delta. So when delta is small, fine. The two schemes then give almost the same solution. But when you start increasing delta, then you may have some differences. And when delta is large, then the 1.5 scheme can totally diverge. Okay, so now we have some tools to approximate the solution. So what about, we are almost ready to estimate the parameters. So again, what is difficult in our case is that it's a continuous process, continuous time process, but we have only discrete observations of V. We don't observe C, and it's hypoelliptic. So all these 3 points make the estimation algorithm more difficult. Why? So I would like to explain why it's more difficult when it's hypoelliptic. Just consider the case of an elliptic system where you observe both coordinates, V and C. And so it's elliptic. My diffusion matrix is of full rank. Then you just apply the discretization scheme like the Euler-Maruyama scheme. You can write the likelihood, the transition density of this scheme, and you derive a contrast, so a pseudo-likelihood formula, just by deriving the log transition density of the scheme. And it has been proven that when you minimize this pseudo-likelihood, this contrast, then you obtain very good estimator, like they are consistent, and you can even prove that they are asymptotically normal, and with a classical rate square root of n delta. So what happens when you work with hypoelliptic SDE? Because the diffusion coefficient is not invertible, you cannot apply the previous contrast. So what I've done with Susan Ditlevsen and also Anya Melnikova does almost the same thing. You can work with Ito-Tailor schemes of higher order, like 1.5 or the local linearization scheme. And you derive the same, you have the transition density, which is Gaussian, you derive the pseudo-likelihood, and you can prove that the estimators are consistent. What is a little bit weird is the rate of convergence of the estimators. So the rate of convergence of the parameters that appear in the second equation is the usual, the standard rate, square root of n delta. But if you look at the rate of convergence of the parameter of the first coordinate, then it's quite different. It's square root of n over delta. Okay, but this was the case where you observe both coordinates, so you totally observe x. What happens when you have only partial observations? So you don't observe C, you only observe V. So the first idea was to try to enter again the class of Hamiltonian SDE. So if I come back to the Fiji-Nagumo example, for example, if I just assume epsilon known, I can change the system and enter the Hamiltonian class as I said it before. Which is nice, because for this class of Hamiltonian SDE, you have a lot of methods that have been proposed, like based on Martingale estimating functions, on Gibbs samplers, so in a Bayesian settings, and on Euler contrast. And what is the idea? So you don't observe, so again here, you don't observe U, but dVt is equal to ut dt. So what you can do is just you replace ut by increments of v, because v is just the integral of u. So if delta is small enough, then the increment should be close to u. And then you just plug in v bar, this approximation of u, in your contrast. So if just you do that directly, it's fine for the parameter of the drift, but you obtain a biased estimator of the diffusion coefficient. And you just need to introduce this weight, which is the order of the noise, and then you obtain an unbiased estimator for sigma. Okay, but what assume if I cannot change the system if I don't know the parameter epsilon or s. Then you cannot apply this trick, so you have to do something else. And I have been working on mainly two directions to try to replace or to estimate the component C that is unobserved. The first one is by using filtering methods, stochastic filtering with particle filters. And the other one is by using optimal control to estimate or to control the best value for C. And another class of methods that we would like to continue studying with Massimiliano is ABC. Here you don't need really to estimate C. You just, because it's a likelihood-free method, as you may know, you just simulate a lot of trajectories for C, and then you estimate the parameters. So I will talk about filtering and optimal control. So for filtering, when the SD is linear, you can use what we call Kalman filter. So in that case, what we want to be able to do is to compute, to approximate this quantity. So it's the expectation of the hidden component C given observations of the first component. Okay, that's the purpose. The purpose is really to approximate these quantities, this kind of expectations. Okay, so when the SD is nonlinear, you cannot use, you cannot apply the Kalman filter, but you can apply particle filtering methods, also called sequential Monte Carlo. So what is the idea? I don't know what you know about particle filter. Maybe you all know a lot of things about this SMC method. Anyway, it's an iterative algorithm. You will simulate k particles. For each of them, you compute a weight, and you approximate this expectation by an empirical measure written here. So how does it work? It's iterative. So at time j, knowing already the values of the particles at time j minus 1, you simulate with proposal distribution Q, you simulate the value at time tj, and then you update the weights such that you approximate, you filter correctly the trajectory. So what is difficult when you work with hypoelliptic SD? It's the fact that it's a degenerate hidden Markov model, in the sense that VC is not Markovian, but only C. VC is Markovian, sorry, but not C alone. So the hidden part is not Markovian. So what you have to do when you compute the weight, you have to be very careful, because the transition kernel is 0 almost everywhere. Anyway, we can do that. That's what we have proposed with Susan Ditlevsen in the elliptic case by using the Euler-Maruyama approximation, and in the hypoelliptic case by using a 1.5 scheme. And what we were able to prove, and I think it's really nice. So again, what we want is to approximate this exact conditional expectation. So it's the expectation, the conditional expectation of C, the second component, given V. Because we use an approximation, a numerical scheme, what we directly estimate without any bias, it's the same quantity, but on the discrete scheme, on the discrete process. So that's what I write with this delta. So here it's a conditional expectation of C given V for the discrete approximate model. And how do we do that? What do we obtain with the particle filter? We obtain this empirical measure. And what we can prove, so in the elliptic case, we were able to prove that the particle filter converges to the approximate conditional expectation very fast. So we have concentration inequalities in that case for any epsilon. And we have more if the step size that you use for the discrete scheme is less than 1 over square root of the number of particles. So you have a link between the number of particles of the particle filter and the step size you use for the discretization. You can also prove the convergence of the particle filter to the exact conditional expectation, which is really nice, because then you know that the contrast that you will compute and you will calculate for statistical estimation is supposed to converge to the true likelihood, thanks to these results. In the hypoelliptic case, it's a nightmare. So with Susan Ditlevsen, we try to prove, so we are able to prove the first result, of course. So you just discretize the system, you work with a discretized version, and then you prove that the particle filter works with the discretized scheme. But if you want to prove the second result, it's much more difficult. And we were not able to prove it for the 1.5 scheme. And my hypothesis, my conjecture is that with the splitting scheme, which is a scheme which has more structural properties, we should be able to prove this second result. Let's see. So some illustrations. So here it's some filtering results on the Fitzhugh-Nagumo. So you have in black the true simulated trajectory, and in gray the filtering obtained by the particle filter. And I think I have also an illustration for Maurice Lockhart. So if you remember well, Maurice Lockhart is highly nonlinear. So you have less precision in the filtering, but it's quite okay. Then the next step is the estimation of the parameters. So now I have a tool, this particle filter, to replace, to update the hidden coordinate C by a particle version. So I can, I'm exactly in the framework of the EM algorithm, and you can also use that for in Bayesian settings, for example. So here, in the case of EM algorithm, you consider two types of data: the observed one, V, and then the complete with data augmentation steps, where you consider V and C. And the purpose of the EM algorithm is to replace the computation of the likelihood by the iteration of these two steps. First, you compute the conditional expectation of the log likelihood of the complete data, V and C. You maximize this expectation, and then you start again. And you can prove that by iterating between these two steps, you obtain a sequence theta hat that converges to a maximum of the likelihood, a local maximum. So here we are not able to compute exactly this E step, so we use a stochastic version of the EM algorithm, which is SAEM. So you split the E step in two steps: the simulation of the trajectory under the filtering distribution. So it's exactly what we obtain with the particle filter. And then you approximate the conditional expectation. So the small trick with SAEM, the stochastic approximation, is that instead of just computing a mean for QM, an empirical mean over all the particles, you compute a weighted mean by keeping the value obtained at the previous iteration of EM and the new value with only one particle taking randomly from the set of particles provided by the particle filter. And then the end step is the same. And what we have seen and proved is that, so you have the typical conditions about the stochastic approximation sequence alpha. And if you choose correctly the number of particles, so you need to increase the number of particles with the iteration of EM to ensure the convergence of the algorithm to a local maximum of the likelihood. And here, to prove that, you really need the previous result about the particle filter. You need to prove that you need this concentration inequalities to prove the convergence of SAE. Okay, so it works quite well. So here you have the results on the Maurice Lockhart data. So all the parameters. So you see it's a stochastic EM. So you have a lot of randomness along the iterations of EM for almost all of them. And at some point, you really start as a stochastic approximation, and you see the convergence of the algorithm to a stationary value. And for the Fiji-Model model, what we have done, we have simulated 100 data sets, and we have compared. So when we assume epsilon known and fixed, so here we have different algorithms, a possible algorithm when you fixed epsilon, and the problem is more difficult when you try also to estimate epsilon. So the true values are here. So you see that when we estimate epsilon, sometimes we'll lose a little bit on some parameters, like on gamma and beta, but it remains quite okay. Okay, and then can I continue or should I stop? I don't know what's. Do I have time to? It's just 3 slides, I think, on optimal.
Yeah, I think that it's fine. Yeah.
I will do it quite quickly. So in the framework of optimal control, you don't consider the quantity to be random in some sense. You just introduce a cost function. So here you say that you want the observation to be close to the approximation of the solution, V tilde, and you introduce what we call a control sequence, UI, which mimics the Brownian process. So it looks like a likelihood, this one, but it's what we call a cost function. And then what you want is you want to obtain the best control sequence U, so like the best realization of the Brownian process in terms of minimizing this cost function. And as soon as you obtain this control, the best control U bar, you just define your estimator by plugging U bar in this cost function. And what is nice is that when you use 1.5 scheme to approximate SDE, this problem of finding the best U, which is a kind of filtering, can be done by what they call the linear quadratic tool in optimal control problems. And it's very well known. You have explicit solution and you can do everything explicitly. Okay, so there is some trick where you can introduce weights, but I will just split that. And so we compare the results obtained with this strategy with SAEM, and it was quite convincing. I mean, the results are almost the same. Okay, so just to conclude, I think we still have some works to do about numerical schemes, and really for me, thanks to Massimiliano and Irene, I discovered these splitting schemes. I think they are very promising, and we can surely do a lot of things in statistics with these schemes. About filtering, we still have things to do theoretically, especially with splitting schemes. And also there are a lot of quite recent literature, especially from van der Meulen, about conditional simulation of hypoelliptic diffusion. So maybe there's also something to do here, coupling this algorithm with statistical algorithm. And this last strategy I presented about optimal control is also quite promising, but I think we have to test this strategy on more complex models. And about parameter estimation, so I have presented a strategy with EM algorithm. We can certainly do something else. Like I just see a recent paper with Hamiltonian MC, and Massimiliano has also looked at ABC algorithm. And we have just started looking at ABC strategy for these models. So I will stop here. Thank you.